Hello again. This is Math 2-115 coming to you from the College of DuPage, and the title of this lecture is Number Theory Applications to Computer Science, Modular Matters Revisited. As always, please be an attentive learner while watching this video. And by way of introduction, I want you to recall what are the integers. The integers are a set of numbers, often denoted by z, and z is equal to, this is the roster of all the integers. It is 0, it is plus or minus 1, it is plus or minus 2, ... and keeps on going. And those are what the integers are. They're the signed whole numbers and 0. A great mathematician named Kronecker once famously said that God created the integers, but all else is the work of mankind. In this section, we're going to introduce several important applications of number theory. We're going to use number theory to generate pseudo-random numbers, an important thing in computer science, to assign memory locations to computer files, to check the digits to detect errors, and in fact you can correct errors in various kinds of identification numbers. And we also will introduce, and this is my main goal in this series of lectures, the subject of cryptography or encryption. Number theory plays an essential role in both classical cryptography, first used thousands of years ago by Julius Caesar, and modern cryptography, which plays an essential role in electronic communications today and off into the future. We'll show how the ideas we develop can be used to design protocols for sharing keys and for sending signed messages. Here, signed doesn't mean plus or minus. It means endorsed, signing it saying, yes, it's really me. Number theory, once considered the purest of math subjects, has become an essential tool in providing computer and internet security. So let's begin with a definition. In fact, we'll have a series of definitions. So if a and b are integers and a does not equal 0, we say that a divides b if there is an integer c such that b equals a times c, or equivalently if b divided by a is an integer. When a divides b, we say that a is a factor or divisor of b, and that b is a multiple of a. This notation, and I know we use this notation for a lot of things, but in this chapter, this notation is a divides b. That's what this means. There's the words, and if you put a slash through it, that means a does not divide b. So let's look at some examples. Does 3 divide 7? Well, no, because 7 over 3 is not an integer. Does 3 divide 12? Yes, because 12 divided by 3 is 4, and 4 is an integer. Example 2 actually has us do a little bit of counting. So let n and d be positive integers. How many positive integers not exceeding n are divisible by d? Well, what's going to happen is that when you look down here and you have positive integers, you say, well, I'm going to have 1d, 2d, 3d, up to, but you don't want to exceed n. And so when you think about what that is, you know that are all integers of the form dk, where I just showed you, where k is a positive integer. Hence, the number of those divisible is the number of integers, k, where 0 is, and I said it was positive integers, so 0 is less than dk is less than or equal to n. So if I divide all the way through by the d, I get that 0 is less than k is less than or equal to n over d. Therefore, there are, and this is the floor function, n over d, positive integers not exceeding n, are divisible by n. Some of the basic properties of divisibility happen here. This is a theorem. You can prove these things. So if a divides b and a divides c, then a divides b plus c. And that's the only one of these that we prove. But if A divides B and if A divides B, then A divides B times C for all integers C. And if A divides B and B divides C, then A divides C. These proofs are not hard proofs, and I would encourage you to do it, but let's look at the proof of number 1. Okay, so suppose that, suppose that A divides B and A divides C. Then from the definition of divisibility, it follows that there are integers S and T, and which are probably different. So B is AS and C is AT. Hence, B plus C is the same thing as AS plus AT. That's equal to A times S plus T, but S plus T is an integer. Therefore, A divides B plus C. So that establishes the theorem. Now, the theorem does have a useful consequence, and it's this corollary. So if A, B, and C are integers, where A does not equal to 0, and such that A divides B and A divides C, then A divides MB plus NC whenever M and N are integers. And so the direct proof again is that if A divides NB and A divides NC when those are integers, then A divides the sum of those two because those are still integers. We also will need the division algorithm. So when an integer is divided by a positive integer, there is a quotient and remainder, and the division algorithm is a theorem. And here's what it says. Let A be an integer and D be another. So A is an integer and D is a positive integer. Then there are unique integers, Q and R, with 0 less than or equal to R less than D, such that A equals DQ plus R. Now we're going to prove this theorem later in our discussions, but it's not really an algorithm because it's really an existence proof. It just is an existence proof. It says there are numbers, and these numbers are unique, such as true. It's an algorithm, gives you an input and a way to get the output to answer the question. So we'll discuss this, but we use this terminology because this is used so often. Now, an important definition, and I think we've talked about this before, but we're talking about it again. We're revisiting this topic. In the equality given in the division algorithm, D is called the divisor, A is called the dividend, Q is called the quotient, and R is called the remainder. And so the notation used to express the quotient and remainder are that Q is equal to A div D, and R equals A mod D. Now this really is a definition really of the modular function. So let's look at some more examples. So what are the quotient and remainder when 101 is divided by 11? Well, you find out that the numbers are 9 and 2. So 101 is equal to 11 times 9 plus 2. So the quotient is 9 and the remainder is 2. Now example 4 though, we're saying what are the quotient and remainder when we have minus 11 is divided by 3. Now you want to be careful here and refer back to the definition. You see minus 11 is equal to 3 times minus 4 plus 1. Hence the quotient when minus 11 is divided by 3 is minus 4, which is equivalent to minus 11 divided by 3, and the remainder is 1. Now note that the reason we were forced to consider it this way is that the remainder cannot be negative. Consequently, the remainder is not minus 2, even though you can make an equation like this, because by our definition, r equal minus 2 does not satisfy r being between 0 and 3. Note that an integer a is divisible by the integer d if and only if the remainder is 0 when a is divided by d. And you want to be careful because different programming languages refer to this differently, and there are different consequences. So be careful about this when you're using different programming languages. Let's now turn our attention to modular arithmetic. So I think this is probably a definition. So if a and b are integers and m is a positive integer, then we say a is congruent to b modulo m, sometimes said mod m, if m divides a minus b. And you have to think about what that means. We use the notation a, and this is 3 lines for congruent to b, in parentheses mod m, to indicate that a is congruent to b modulo m. We say is congruent to b modulo m is a congruence, and that m is the modulus. Then the plural of this in Latin is moduli. If a and b are not congruent, we could write the congruent symbol with a slash through it. Although both notations include mod, this one we just did, and this one, they represent fundamentally different concepts. The first represents a relationship, and so it's a relation, and in fact it will be an equivalence relationship on the set of integers, whereas the second is just a function that you would call in a software program. But they're closely related, as you can see from the theorems. In fact, this theorem says that those two things really are saying the same thing. Let a and b be integers and m a positive integer. We say that a is congruent to b mod m if and only if these two functions from your software are congruent. So the proof of this theorem is not something we're going to spend time for, but those two things are equivalent because that's if and only if. So I could ask you questions. Is 17 congruent to 5 mod 6? And you say, yes it is, because 6 divides 17 minus 5, which is 12. So that means that 17 is congruent to 5 mod 6. However, because, and this is the second one, checking if 24 and 14 are congruent mod 6, 24 minus 14 is 10, and that's not divisible by 6. So those two things are not equivalent. Here's another theorem that is a useful way to work with congruences. Let m be a positive integer. The integers a and b are congruent modulo m if and only if there's a number k such that a equal b plus k m. And if you start looking at this for a while, you see, oh, this is tied to the division algorithm as we defined it, and here's the proof. So if a is congruent to b mod m, then we know that m divides a minus b, and that means by the division algorithm that there exists a k such that a minus b is equal to km, so that a is equal to b plus km. And conversely, if there is a number, because this is an if and only if, we have to go both ways, number k such that that is true, then km equal a minus b, so m divides a minus b, so a is congruent to m, a is congruent to b rather, mod m. And looking back on what we said, what we studied before when we were talking about functions and relations, the set of all integers congruent to an integer a mod m is called a congruence class or equivalence class of a mod m. Now we haven't really proven this is an equivalence class, but certainly it is, because certainly a is congruent to a mod m. If a is congruent to b mod m, then b is congruent to a mod m. And if a is congruent to b mod m and b is congruent to c mod m, then a is congruent to c mod m. So it's reflexive, symmetric, and transitive. That makes it an equivalence relationship. And so that means that this equivalence relation induces a partition on the integers, and so they're m pairwise disjoint equivalence classes mod m, and their union is a set of all integers. Now, multiplication and addition preserve congruence, and so here's a theorem and also a proof. So if we let m be a positive integer, if a is congruent to b mod m and c is congruent to d mod m, then a plus b is congruent to b plus c mod m, and a times c is congruent to b times d mod m. And the proof follows very directly, because let's look at the sum. So b plus d under our assumptions here is equal to A plus SM plus C plus TM, but I can reorganize it this way. And BD is equal to this times this, and I can reorganize it this way. Therefore, this congruence exists and this congruence exists. It really just follows from the definitions and a little bit of arithmetic. Now, because 7 is congruent to 5, because 7 is congruent to 2 mod 5 and 11 is congruent to 1 mod 5, it follows that 18, the sum, is congruent to 3 mod 5, which is the sum of 2 and 1, and if you multiply them, it's 77 would be congruent to 2 mod 5. Now, you have to be careful when working with congruences, although we're going to show you that many properties that you would expect to be true are, but some are not. For example, and this is a very important one, if A times C is congruent to B times C, if these were equality, you could say, oh, that means that A equals B. But that congruence is not true. It may be false, and we'll talk more about that later. And similarly, if A is congruent to B and C is congruent to D, A to the C is not congruent to B to the D in general. It may be false. And we'll discuss conditions for this exponentiation and this cancellation property later. I'm going to state a corollary, second corollary to one that we already talked about. So if we let m be a positive integer and a and b also be integers, then a plus b mod m is equal to a mod m plus b mod m mod m. And ab mod m is equal to a mod m times b mod m mod m. And you have to think about this, but this theorem or this corollary is about the equivalent functional definition. And here's the proof, and the proof is kind of obvious. It follows directly from the last two congruences that we used in the previous theorem. Now let's move on to talking about modular arithmetic then. So we can define on these equivalence classes, then we can say take A and B and add them mod m, or multiply them mod m. This is the definition of addition, and this is the definition of multiplication. Okay, so let's apply these definitions. So we're going to use the definition of addition and multiplication in Z sub n, and that's what we define this set to be. To find 7 plus 9 added together in mod 11. Well, that's going to be 16, which is congruent to 5 mod 11, and 7 times 9 is 63, and that is 63 is equivalent to 8 mod 11. So the answer to these are 5 and 8. And these operations satisfy many of the same properties of ordinary addition, although, as I said before, addition and multiplication, but you have to be careful with cancellation and exponentiation and sometimes other things. So the operations plus and multiply in the modular arithmetic satisfy many of the same conditions. So if A and B belong to Z mod m, these set of equivalence classes, then you can add and multiply things and you still get something in Zm. If A, B, and C belong to that, then addition is associative, the grouping is okay, and multiplication is also associative. They are commutative, the order doesn't matter. The sum this way is the same as the sum this way. The product this way is the same as the product this way. There are identity elements. 0 and 1 are the identity elements for addition and multiplication mod m. That is, if A belongs to the C equivalence classes, then you can add modular arithmetic and you add 0 and you will get A back again. And if you take 1 and multiply something, you will get A back again. There are additive inverses. But this is a little bit different because you don't have 3 and minus 3. So if A does not equal 0 belongs to Zm, then M minus A is the additive inverse. And 0 is its own additive inverse. That is, A added with modular arithmetic to M minus A is equal to 0. And 0 plus 0 is 0. We also have a distributive property. And so if A, B, and C belong to Zm, then you can distribute and you get the same results. So we're distributing modular multiplication over modular addition. These proofs are not hard, but there's an important thing that you want to note. Note that we have listed a property that every element has an additive inverse, but there is not an analogous property for multiplicative inverses has been included. This is because multiplicative inverses do not always exist mod m. There is no multiplicative inverse of 2 mod 6. You can verify that, and we'll talk more about that later, but let me continue here, and let's see. These properties follow from the properties that we developed, and in the more fancy math, we talk about those properties of multiplication and addition combined with the set satisfy the properties. It's said to be a commutative group. And then when you add multiplication, it is called a commutative ring. So the set of integers with ordinary addition and multiplication also form a commutative ring. And those are studied in abstract algebra. I said we'd revisit this, and this is also looking ahead. So here is mod 4. That means I have 0, 1, 2, and 3, 0, 1, 2, and 3. And here is multiplication for that. And if you look and follow the calculations, you'll notice that, yes, 1 is a multiplicative identity, but 2, looking across here, has no multiplicative inverse. Look at another example. This is mod 7. Notice I have 0, 1, 2, 3, 4, 5, 6. But when I do this, if I check, everything except 0 has a multiplicative inverse. 1's multiplicative inverse is 1. 2's multiplicative inverse is 4. 3's multiplicative inverse is 5. 4's multiplicative inverse is 2. 5's multiplicative inverse is 3. And 6's multiplicative inverse is 1. And so you say, well, what's the difference between mod 4 and mod 7? And if you're guessing that 7 is a prime number, you have some good intuition. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless y'all.